Subscribe to our channel and press the bell icon to never miss any update from Gradeup.
Hello everyone, hope you all are doing good with your preparation. And so the exam is close, so you must be solving a lot of questions and revising the concepts which you have learned. So this is Swarit Dwivedi. Today I'll be discussing with you all guys about JEE Main 2017 question paper, and in particular, if you know me, we solve the chemistry questions of the previous year papers. So let's begin, and in this screencast I'll be solving question number 1 to question number 10th. So okay, let's start with the discussion of the difficulty level of these questions. So in question number 1 to question number 10, most of the questions are easy, right? Most of the questions are easy. 4 questions of them are like medium, you can tell them. Then also they are not tough, but yep, in the next screencast you'll be facing some tough questions. But as you know, the chemistry question paper is generally easier than mathematics and physics, and if you have a good strategy and you prepare well, you can save some time as well to to give that time to mathematics and physics where it is required. So yep, let's start with the question number 1. So it's a lengthy, it looks like a big question to read, but it's a fairly simple question. So you have given a reaction, right? C graphite and reaction with O2 gives CO2, and the heat of the reaction has already been mentioned here. And you have another reaction for, let's say I call the first reaction as our number 1 reaction, and the second reaction also I'll just numerically assign them a number. And the heat of reaction has also been given for this reaction, and we have another reaction which is reaction number 3. Okay, so heat of reaction has been given for this reaction as well. Now based on the above thermochemical equations, the value of delta heat of reaction at 298 Kelvin for this reaction will be. Now what we need, we want to get to this reaction, right? This thing. Okay, and so how can we get it? So we want graphite plus 2 times H2 gives CH4. So somehow we need to rearrange these 1, 2 and 3 to get to this, right? Getting to this we need 1, right? If we take first reaction, right, because graphite we need, right? And we need H2, okay, and we need H2 2 times. So let's just add the second reaction 2 times, right? So let me just tell you that this is a reaction 2 times the second reaction. Okay, so yep, and then let me just okay, all right, let me just add the third reaction, right? Add the third reaction here, and let's see where do we get. Okay, so you have the first reaction, so you have C plus O2 gives CO2, right? 2 times the second reaction, 2H2 plus half. Okay, so 2 times 2H2 plus O2 gives 2H2O, right? And then we add the third reaction, CO2 plus 2H2O gives CH4 plus 2O2. So you see here, from here this 2O2, this O2O2 will be cancelled out, and this 2H2O and this 2H2O will be cancelled out. When you'll add this reaction, right, finally you will come up to, okay, and this CO2 and CO2 will also be cancelled out, right? So finally you come up to C plus 2H2, right, gives CH4, which you wanted. So you need to take the first reaction add 2 times of second reaction, and then add the third reaction, and you will come up to your product. So the heat of reactions will also be added in the same amount for the third reaction. So the heat of reaction for the third reaction, all right, so heat of reaction for the third reaction, okay, will be for the mentioned reaction actually will be 2 times, all right, sorry, will be minus 393.5, which is the heat of reaction of the first reaction, plus 2 times heat of reaction of the second reaction, right? According to this thing, heat of reaction of the second reaction, which is minus 285.8, plus heat of reaction of the third reaction, which is 890.3. And when you solve this thing, you will come up to, you'll see that the answer, this thing is equivalent to minus 74.8, right? So the A part here is correct. You just need to rearrange these three equations, just add them up, and get to the equation which has been asked. And how you do that, you just try to take the compounds and try to cancel out the compounds which is not required in the final reaction. Okay, and then you add the heat of reactions according to according to the ratio in which you have added these reactions, and then you'll be up with the answer. All right, so let's move on to the next question. Now 1 gram of carbonate, okay, so 1 gram of carbonate, which is M2CO3, okay, so there is some carbonate which is M2CO3 on treatment with excess HCl produces 0.01186 moles of CO2. Okay, so let's say there is a carbonate which is like this, and its reaction with HCl produces CO2 is fine. So the number of carbons will be there on the left hand side, equivalent number of CO2s will be produced. Plus, obviously, if it's a metal and CO2 is there, so you'll get MCl, metal chloride, right? Right. And why you get MCl? So you can ask this question because here the metal valency seems to be 1. Okay, so MCl you'll get, and plus you get some H2O. So you'll get here twice MCl and you'll get a single H2O. So this is a balanced reaction. You can, all right, this is not a balanced reaction. Now this is a balanced reaction. Okay, so what you'll do here, now you see the number of metal carbonates you had, right? The exact number of exact moles of CO2 you are getting, because here the stoichiometry of the reaction suggests the number of M2CO3 you will be having, the exact number of CO2 you will be getting. Okay, so what you do here now, you if it produces 0.01186 moles, if 0.01186 moles of CO2 is produced, that means 0.01186 moles of M2CO3 would have been used, because the exact number of CO2 is produced. So now you know the number of moles of M2CO3, right, is 0.01186. Okay, and you have taken 1 gram of this, because number of moles is just weight upon molecular weight, and weight that you have used 1 gram, right? You have used 1 gram, that thing so the molar mass is nothing but 1 by 0.01186. all right, and how do you get to know this thing? So it's fairly simple calculation. You just have it here 100, and then like 1.186. So it is a bit less than 100. So yep, so which is the correct option? It's 84.3, right? Okay, so let's move on to the next question. Now delta U is equal to, right? Delta U is what? So let's let's see about this question. Delta U is equals to Q plus W, right? This is your law of thermodynamics tells you. And now it is telling delta U is equals to adiabatic work. So in case of adiabatic, your Q is 0. In case of an adiabatic process, your Q is 0. So if a process is adiabatic, so delta U for a adiabatic process, okay, is equivalent to the work done of that process, because Q in that case is 0. This is a fairly simple question. The first option suggests you the answer, and you can see for the other options as well. If you would have taken a isothermal work, so isothermal doesn't mean that Q is 0, so it doesn't mean that equivalent to the work done. Isochoric work, in isochoric, then again you don't have the same thing. Isobaric, you don't have the same thing. Okay, so the first part is correct because Q is 0 in case of adiabatic. That's why the delta U of adiabatic process is equivalent to its work done. All right. Now the Tyndall effect. Alright, so the Tyndall effect is observed only when the following conditions are satisfied. So here you can see the conditions which are given here. So the diameter of the dispersed particle is much smaller than the wavelength of light used. Diameter of the dispersed particle is not much smaller than the wavelength of the light used. So yep, so here you are just having this thing. These two options suggest that the diameter of the particle which has been used and its comparison to the wavelength of the light used, right? The wavelength of the light used, okay, and the diameter of the particle. So they are comparing that are they comparable or not. So one of these options will be true. Okay, and the refractive indices of the dispersed phase and dispersion medium are almost similar in the magnitude, right? So there will be a dispersed phase, and there will be a, let's say, there will be a dispersed phase and there will be a dispersion medium. So it is telling that the refractive index of the light, the refractive index in these two medium will be almost similar or will differ in greatly in magnitude. So one of A and B will be correct and one of C and D will be correct. You have to identify which of them. So it's like a very simple thing. So why it's a simple thing, I'll tell you. So you can utilize your general knowledge about colloidal solution and you can answer this question even if you know nothing about Tyndall effect. So Tyndall effect you generally see in colloidal solutions, right? And what are colloidal solution? We have like a bit bigger particles in colloidal solution. Colloidal solutions are not like we can see them with light, so they are like bigger particle colloidal solutions. So bigger particle means greater in magnitude, so means it will be comparable to the wavelength of light. And the smaller particles, like the solutions, the normal solution, we cannot see, but the bigger particle we can see because they are comparable to the wavelength of light. So in that case, B option is correct. And the refractive indices of the dispersed phase are almost similar. If they'll be similar, so what we want to observe Tyndall effect, we want the light to go through one medium and to either reflect or scatter, so that we can just see the light, we can see the particles, we can see the particles in the solution. But if the light transmits, then it's harder to see them. So when the two mediums differ greatly in magnitude, then it is easier for light to scatter and reflect back. So in that case, the D option is correct, right? So here the B option and the D option is correct. So the D part is the answer of this question, right? Okay. So a metal crystallizes in a phase. Okay, this type of question every year you tend to get one. Okay, most of the time it's BCC. This year it's FCC. So let's discuss this one. So yeah, metal crystallizes in a face-centered cubic structure. So what's a face-centered cubic structure? You have like this kind of a geometry. Let me draw. Okay, all right. So yep, let me draw it completely. All right, so that you can have a basic idea about it. So I'm just worried that I can draw it neatly or not. All right, looks fine. All right, so one more plane I need to draw. Okay, looks okay, not good but not bad as well. So all right, so this is like face-centered cubic. You have an atom here, and then you have FCC, so you have atoms here at the face centers as well, and you have atoms at the corner, at the vertices also. So what happens in a face-centered cubic cell? In a face-centered cubic cell, all the atoms present at a face are in touch with each other. So if I draw a face of this, this kind of lattice arrangement, I'll see that this atom present at the vertices, which is this atom, and the atom which is at the center of the face, which will be this atom, and the other atom which will be at the vertices again, which will be this atom, are touching each other, right? So if I draw this line which is the diagonal of this face, then they are all in line with each other. So this will, if this is the radius of the atom which is in FCC arrangement, so this length will be 2r, and another this length will be r. So actually the diagonal of this face, if the side length of this cube is a, right, so the side unit length is a, if the side length of this cube is a, then this diagonal will be how much? Will be root 2 times a, obviously, yeah, the Pythagoras, right? And this is equivalent to 4 times r plus 2r plus r. So it's asking that the right, so the closest approach between two atoms will be, so what is the closest approach between two atoms? This plus this, center to center distance. This is the closest approach. So this is basically 2r. So 2r is equivalent to root 2 times a by 2, which is r is equals to 1 by root 2a. So a by root 2, which is B option. Alright. Okay. Given Cl2 to Cl negative, so let me just correct it. Cl2 to Cl negative is equals to 1.36 volt. Cr3 plus to Cr is minus 0.74. Okay, Cr2O72 negative, right, to Cr3 plus is this much, and MnO4 negative to Mn plus is this much. So among the following the strongest reducing agent is. So these are like these are the standard reduction potentials that has been given to you, or the reduction potential simply has been given to you here. And among the following the strongest reducing agent is. So what is the strongest reducing agent? So it should be easily oxidized. If it is a strong reducing agent, so it should be easily oxidized. Easily oxidizable means lower the reduction potential, right? Easily oxidizable means lower the reduction potential. So among the following, which is having the lowest reduction potential? Simply the Cr3 plus 2 Cr1. Alright, so among the following, the strongest reducing agent is Cr3 plus, because it has the lowest reduction potential, so it is easily oxidizable, so it is the strongest reducing agent, right? All right, move on. Now the freezing point of benzene decreases by 0.45 degrees centigrade. Wait, so the freezing point of benzene decreases by 0.45 degrees centigrade. So it's in this question the delta T freezing, right? So the delta T freezing, which is the the depression in the freezing point, will be equivalent to I times Kf times M, right? Where this M is the molality of the solution. Okay, so now how do you calculate I? I is equals to 1 plus 1 by 2 minus 1 times alpha. Alright, is that clear? And alpha is your dissociation factor, dissociation or association. So the freezing point of benzene is by decreases by 0.45. So TF is given as 0.45. When 0.2 gram of acetic acid is added to 20 grams of benzene. So from here you can find the molality as 2.2 gram of acetic acid. So here the weight of acetic acid divided by added in 20 grams of benzene. So 20, alright, into 10 to the power minus 3, because you have to have it here in kg. Alright, so here you put the weight of acetic acid. Alright, so you get the molality here. So what is acetic acid? CH3COOH. Alright, so you put the weight here. And then if the acetic acid associates to form the dimer in benzene, so what happens with acetic acid? Acetic acid forms dimer in benzene. So two of these acetic acid tend to form this structure when they are in benzene. So the percentage association of acetic acid in benzene will be, right? So it wants to know the association factor in percentage. That's a nice question. Okay, so Kf has been given, T has been given, you need to find out I you'll be finding out with here. So here this I is equals to 1 minus alpha by 2. Alright, because here the N is 2. You have taken N2 here because it's forming a dimer. Alright, so now you put these values here. You put this 0.45 is equals to I, which is 1 minus alpha by 2, and then your your Kf, which is 5.12, and then your molality, which is 0.2 by 60, right, divided by 20 into 10 to the power minus 3. When you solve this whole equation, you'll boil down to, or just let's solve it. It's fairly, we can solve it, I guess. So it's 0.45 into 20 into 60, right, into 10 to the power minus 3 divided by 0.2, right, and to 5.12 is equals to 1 minus alpha by 2. So this whole thing here, right, if you calculate it, it's near about 0.527, and your alpha then will come out to be 0.927. 0.945 if we'll calculate it. So alpha is 0.945. So the percentage, the percentage association will be 94.6, nearly 94.6. So that is your correct option here. Some a bit calculation is there, but you can do it very easily. Like if you want to approximate the calculation, this will be 0.1. Then here you have 10, and then again you can take it as 100, and take this 100 and take this 0 from here. You remove this 10 to the power minus 3, and then you have 6 here, and you have 0.45 here. You can easily do the 6 times of 0.45, because it will be 2.7, right? You have 2.7 here, you have 5.12 here, so it's just nearly 1/2 difference. Okay, it's nearly one. So you can try to approximate, because the options are like pretty much difference at the the difference is at the order of till 10. Okay, the difference. So you can easily identify the correct option by doing a bit approximation as well. Okay, so now the eighth question: the radius of the second Bohr orbit of the hydrogen atom is. Okay, so the hydrogen atom, so Bohr orbit, so there are a lot of constants which are unnecessarily given to you, because you are supposed to remember the first Bohr orbit, right? Or else you always have to track down the whole formula and calculate n square, h square, epsilon naught, and whatsoever. Okay, but if you know the formula, not for hydrogen atom, for any atom, for its radius, which is the Bohr radius, is is r naught times n square by z square, right? Or okay, I guess n square by z. All right, so now you don't have to worry actually about z, because z is 1 here, because you are talking about a hydrogen atom. So r is equals to r naught, which is 0.529 angstrom, into n square. And what is n in this case? The radius of is second Bohr orbit, right? So n is 2 in this case, n square, which is 2. So r is equals to 4 times 0.529 into 10 to the power minus 10 meter. So here, if you multiply 4 by here, so you'll get 2.12 into 10 to the power minus 10 meter. Here, the options are in angstrom, so it's just 2.12 angstrom. So your B part here is correct option. Right? This is a fairly simple question. And if you don't remember R naught, then you obviously need to struggle with all the nasty calculations, and eventually you will calculate R naught from here. So I don't know what's not the point to remember it. Okay, so let's move on. So two reactions R1 and R2 have identical pre-exponential factors. So if I talk about K1 is equals to A e to the power minus E1 by RT. So identical pre-exponential factor means this A will be same, E2 by RT, right? The activation energy R1 exceeds of R2, so by 10 kilojoule. So activation energy of R1 means E1 exceeds of R2 minus E2 is 10 kilojoule, right? 10 to the power 3 joule per mole, right? Okay. If K1 and K2 are the rate constants of R1 and R2 respectively, right? We have it here at 300 Kelvin. So T is again 300 Kelvin. Then ln K2 by K1 is. So, okay. So we don't need to do anything. We just need to divide K1 by K2 is equals to a will be cancelled, e to the power minus e1 minus e2. Oh, okay, so alright, so why to do this? They ask k2 by k1, right? So you divide k2 by k1 is equals to, yep, a will be cancelled again, and here if you see, because there is a minus sign, so even though it will be minus of e2 minus e1, you'll eventually get e1 minus e2. E1 minus e2 divided by RT. Okay, so eventually, okay, so if you take ln now, taking ln here, so if you take ln here, ln k2 by k1, all right, you'll get down to e, okay, now the e will go and you'll get to 10 into 10 to the power 3 joule per, and r is 8.314 joule per mole per Kelvin, into your T is 300 right now. Alright, so yep, so here if you solve this whole thing, and if you try to solve this thing, right, then you get to what? Okay, so okay, so you solve this thing, it will be, I guess it will be 3.9 something, right? Because okay, so now it will be 100 and this will be cancelled out with this, and if you see here, so 3 times of will be 2, 3, 4, 9, right? Okay, so it will be like 24.9, like so near about, okay, so it's near about 25, right? So this term is nearly 25, and if you divide 100 by 25, you get nearly 4, means like 3.9 something or 4.1 something. So you get the answer here as 4. Okay, so the 9th question comes down to option B part, which is 4. Now, this is like the easiest question you can get from ionic equilibrium. I don't know how they find this much easy question from ionic equilibrium. They usually ask a bit tough questions. So, yeah, so pKa of a weak acid and pKb of a weak base. So, both are weak acid and weak base are respectively. So, pKa, okay, is equals to 3.2, your pkb is equals to 3.4 respectively, obviously. So the pH of the solution will be, so pH of the solution of your weak acid weak base is 1 by 2 times pkw plus pka plus pkb, that's all. Sorry, minus pkb, right? That's all you need to do, nothing else. That's all you need to do. So is equals to 0.5, which is 1 by 2, plus 14 plus 3.2 minus 3.4. So you obviously get it down as 0.5 times 14 minus 0.2 is 13.8, I guess so, and you get it down to 6.9. So that is your correct option, D part. Simplest question, no calculations so whatsoever as well. So that's good. So here are the first 10 questions of JEE Mains 2017 examination, and hope to see you soon for the second screencast. This is Soyud Dwivedi signing off. Make sure you download the download the Gradeup app on Google Play. It has new tests every day, complete solution chapters, notes are available on Gradeup app, and you can always discuss your queries with your fellow students as well as the experts from our team. So go ahead and download the download the Gradeup app if you haven't downloaded yet. And this is Soyud Dwivedi signing off. Let's catch up in the next screencast. Thank you.